Hello students, it's Mr. Bornheimer, and I'm just going to do a quick short video here talking about the impulse momentum theorem. The impulse momentum theorem we kind of introduced today in class, and I'm just going to kind of do a brief recap. When Newton first started studying his laws of physics, which at the time weren't really laws, they were these concepts that Newton had kind of put together from things he had seen, one of those laws, F equals ma, okay, kind of had other connotations, connotations we hadn't talked about, or significance we hadn't talked about yet in class. So what we're going to do today is we're going to take Newton's second law, and I should probably put the little arrows above the force and the acceleration to indicate that these are vectors. But what we're going to do is we're going to kind of wrap it, and we're going to kind of present Newton's second law in terms of momentum. So first thing we need to do is we need to kind of look at this variable acceleration. And what we want to do is we're going to replace it. We're not going to replace it with something entirely different. We're actually going to replace it with a value or variables that represent acceleration, but not necessarily maybe as blatantly obvious. So what we're going to do is we're going to go ahead and just, this is like the first step in our problem. Well, this will be our second step. And this is going to be F equals M, but instead of A, I'm going to do delta V over delta t. In essence, this is kind of like the definition of average acceleration, where you have a change in velocity over a change in time. Now, the third step in this particular problem would be to try and get rid of the fraction, or move delta t to one side of the equation, the other side of the equation, as a matter of fact, in order to kind of get everything in a nice linear representation. So to do this, we could go ahead and multiply both sides by delta t. And when we multiply both sides by delta t, what we see happen is that the t's on the right-hand side cancel out. So this ultimately will turn into F delta t equals m delta v. And this is the impulse momentum theorem. And it is a representation of both impulse and momentum. Now, I do want to take this a step further briefly in this video, and I really want to address the idea of what is impulse and how does it relate to momentum. So it's not going to take very long, but here's how that goes. So impulse is F delta t. It's that first part of the impulse momentum theorem. And what it is how you have a force kind of alters the momentum of an object and sometimes even stops that object, and that force is applied in a very short period of time. This idea of F delta t is equal to the impulse in a given situation. Now, that being said, the impulse is equal to the change in momentum. So if you know what the change in momentum is, you can find impulse because they're equal to one another. The variables we could use here would be I is equal to delta rho, the Greek letter rho here to represent the variable for momentum. And so F delta t is I, so F delta t is I, and it's equal to a change in momentum, which really is momentum final minus momentum initial. And of course, these are vector quantities, so I want to go ahead and put the arrows above everything that deserves an arrow, okay, to represent that it's not both only a magnitude, but also direction is important. So what we see happening here is that we have the impulse, F delta t, is equal to the change in momentum. Now imagine for a moment I have these two hands and I'm going to clap, okay? Now, my hands, this would be my left, this would be my right. To you, they would probably look opposite. They both have mass, and when I move them towards each other, they both have velocity, meaning that they have momentum. move this hand this direction, this hand this direction, and they have momentum. However, when they collide and come together, they stop. Okay, so there's a velocity change there. And because they stop, they're going from having momentum to having no momentum. That is a change in momentum. Now, this change in momentum is the result of an impulse. Impulse, like I said on that previous slide, is F delta T. Well, in order for the two hands to come to a stop, there has to be some force that is being applied over some period of time to stop the momentum of either hand. Now, if the momentum of this hand was greater and then this one, then it would look like this, okay, where it would dominate. Or if it was opposite, it would look like that. But the momentum is equal and opposite, meaning that they have different directions, and when they collide, they come to a stop. And so because the hands come to a stop, there's a change in momentum, and it's as a result of this hand exerting a force on that hand and vice versa, and it happening in a very short period of time. Usually when we're looking at momentum and impulse problems, or the momentum impulse theorem, we look at time as being a very short quantity. Okay? And time being a very short quantity means oftentimes that the force is quite extreme. So, there you have it. The impulse momentum theorem. F delta T is equal to M delta V, also can be written as F delta T is equal to M, and you can expand that delta V, VF minus VI, or V2 minus V1, if that's what you're more familiar with. Or you could also even go so far as to apply the distributive property here to these two, distribute the mass through, and you end up with F delta T is equal to mVF minus mVI. However, mv is momentum. Okay, momentum is equal to m mass times velocity. So really this is momentum final and this is momentum initial. So you end up with the final form of the equation, F delta T equals momentum final minus momentum initial. These four representations of this equation can be very useful to you. So I highly recommend that you star or take a picture or screen capture this particular slide in general, just so you have it and maybe put it in your notes. That ends this presentation. I hope that this has helped maybe clarify any issues you've had with the impulse momentum theorem. And if you have any questions, you can go ahead and contact me by either messaging me through YouTube, or you can go to my website, bclassroom.com, and you can get a hold of me that way. Thank you for watching, and I hope you have a great day.